Okay, so we left off part 2 talking about what delta G tells you. If delta G is negative, the reaction is spontaneous. If delta G is positive, the reaction is non-spontaneous. Now here is a lovely little table relating delta H, delta S, and delta G all together. I cannot emphasize enough how helpful it will be to you to know this table, or at least be able to derive this table on your own. Me personally, I've never been much of a memorizer. I'm more about, taking a formula and applying it to a situation. And so I would rather just know how to work this out from the formula. But if you are a memorizer, then this is a table that you should commit to memory. So, first, if delta G is negative, the only way that that can happen is, well, there's a couple of ways actually that you can get delta G to be negative, but the only way to guarantee that your reaction will be spontaneous all the time, no matter what temperature you're at, is if both of these values contribute to the negativity of delta G. Well, since delta H is by itself, if delta H is negative, and then since we're subtracting, we want this whole thing to be positive. So if delta S value is positive and delta H value is negative, then delta G will always be spontaneous. No matter what the temperature is, this reaction will always move in a forward direction. Well, if you have the opposite true, where delta H is positive and delta S is negative, well, then that's going to make this whole guy be negative, which when you subtract a negative, that makes it positive. So you have a positive plus a positive, that means delta G is going to be positive. And so what that means is that if delta H is positive and delta S is negative, no matter what you try to do, this reaction will not be spontaneous. And just a refresher on what each of these means. Delta G determines spontaneity. Delta H determines whether or not your reaction is endo or exothermic. A positive delta H is endothermic, a negative delta H is exothermic. And then delta S is a measurement of the disorder of a system. And so if delta S is positive, then the disorder has increased. It's gotten messier. If the delta S is negative, then that means the reaction has gotten cleaner, has gotten more ordered. And so there are some situations where a reaction will be spontaneous at only certain temperatures, whether it's low or high. And again, just look at the reaction for this. So if delta H is negative, so I'm going to erase, just kind of cross it. I really wish I had an eraser on this. So if delta H is negative, and then let's say delta S was also negative. So we are subtracting a negative, which means we're adding a positive. And the only way that we're going to get delta G to be negative, to be spontaneous, is if delta H is bigger than this positive value, which means we need to have a low temperature. So the only way that delta G is going to be negative for this situation where both H and S changes are negative is if we have a low temperature. That way it keeps this whole thing small, so we are just adding a small amount to a negative number. And then the flip side of that, if both of these guys are positive, then that means we need this value subtracting a positive value to basically overpower the delta H, and so we need temperature to be high if we want this reaction to be spontaneous. Because remember, anytime G is negative, it's spontaneous. If G is positive, then it's if the change in G is positive, then it's non-spontaneous. But seriously, know this table. It will help you so much whenever you get to these questions on the AP exam. So just a little like qualitative kind of explanation thing is delta G for a burning campfire positive or negative, explain citing the positive or negative signs of delta H and delta S for the process, and then the last part is there a temperature at which delta G for a burning campfire will change sign? So explain. So we have a burning campfire. Let's see, let's draw some logs, draw another log. Don't laugh at my drawings. And then let's have another log just going across here. And then it's on fire. There we have a fire. It's not a bad fire, actually. I gotta say, I'm kind of proud of that. Anyways, so we know that delta G is equal to delta H minus T delta S. So we're going to use the signs on these guys to help us figure out the sign on delta H. So the easiest one is probably the delta H. When you sit next to a fire, you get warm. And so that means the fire itself is releasing heat, which makes this an exothermic process, which makes delta H negative. Now on to delta S. Well, what's going on with the disorder of the system? When we begin, we have these nice, neat logs. They are all put together in a nice, clean kind of situation. And after it's done, we've produced gases, we've produced water vapor and carbon dioxide, and we've got messy ashes. And we end up with a lot more stuff, not mass stuff. We can't create mass, but we can create a stuff. A lot more mess than we started with. And so that means the disorder of this system has increased. And so delta S is going to be positive. And so if you remember from the table on the slide before, and if you don't, pause this, rewind it, look at the table, and then come back to this, you know that anytime we have a negative delta H and a positive delta S, that delta G is going to be negative no matter what. It doesn't matter what the temperature is, delta G will be negative. So is delta G for a burning campfire positive or negative? It is negative because it is both an exothermic and an entropically increasing, I guess, if you want to say that. I'm not even sure if that's the right word, but the entropy increases and it's releasing heat. That causes delta G to always be negative, which means this is always a spontaneous process, and there is no temperature at which delta G will become positive. Now, some of you might be going, hey, wait. A campfire is a spontaneous process? No. Random logs in the forest don't just burst into flames. But the decomposition of the logs into carbon dioxide and water vapor and, whatever other stuff is left over, that is spontaneous. The only thing that the fire does is speed up the spontaneous process of basic decomposition. And you're probably going, wait a minute, decomposition is not an exothermic process. If you have ever been anywhere near a compost pile or a dump in general, you know that decomposition is actually quite an exothermic process because compost piles, they get warm. They actually get very warm. And if you have a compost pile in the dead of winter, you can actually see it sometimes giving off steam because of the temperature difference between the compost pile and the air. So yes, decomposition is quite an exothermic process. All right, now let's take delta G and carry it on one more step and relate delta G to equilibrium. And we're going to go ahead and bring back some K. Oh my gosh, I thought we were done with K. No, you're never done with K in the wonderful world of chemistry. You can actually calculate free energy at non-standard conditions, meaning maybe not 298 Kelvin or maybe not 1 atmosphere, by using this little formula right here. And this is saying that delta G is equal to the standard delta G plus the correction for the temperature, and this is probably going to end up being the correction for the pressure. Remember that Q is it uses the same equilibrium expression as K, except the numbers that get plugged into that expression are the values, the concentrations, or the pressures, or whatever of where you are at right now. Not where you are necessarily at equilibrium, but where you are right now. And just a little heads up, because G is measured in kilojoules per mole, we actually have to use the more physicsy version of R, the 8.314 joules per mole Kelvin. And because delta G is measured in kilojoules, I usually, instead of using this, I will use 0.008314 kilojoules per mole Kelvin, just so that it goes ahead and it matches. And then if you do so happen to be at equilibrium, well, that's the point at which Q is equal to K, and that the delta G of the particular situation is going to be equal to 0. So you could actually find out the delta G under standard conditions using yet another formula. So this makes the third formula that we have for calculating delta G. And in this case, it's if we are given equilibrium information, we can find delta G from that. And you just take negative R, same R right here, temperature in Kelvin, times the natural log of whatever the equilibrium value is. And I think at that point, I'm going to go ahead and call this one quits. And it looks like we're going to have a part 4.